What was the answer for this question? What answer did you get over here for this one? Answers 4. Very good. So 4 is the correct answer. 4 is the correct answer for this question. See, if we start doing this, so we have done over here. So 0, 1, we are at 0, 1 and our input is 1. So if input is 1, output is 0. And your next state, you can see it is 0, 1 only. Okay, you will be remaining at 0, 1 only. Okay, fine. Next is what? Present state is 0, 1 and you give 0. So when you give 0, output is 0 and you go what? 1, 0. Okay, we were at 1, 0, not 0, 1. Yes. So we were at 1, 0. When we apply input 1, output is 1 and we go to 1, 1. Now look, present state is 1, 1. Okay, and input is 0. So if we apply input 0, output is 0 and we go to 0, 1. Output is 0. Next what we have? It is 0, 1. See, we are at 0, 1 and our input is 1. So input when it is 1, we are at the same state and output is also 0. Okay, look now. So over here we are at 0, 1, input is 1. So we will go to, wait, so input is once again 1. So we will remain at 0, 1 only and output will be 0. Okay, we are at 0, 1, input is 0, output is 0 and we move to 1, 0. Okay, so we are at 1, 0, input is 1, so output will be 1 and we go to 1, 1. Next is 1, 1, we are at 1, 1, input is 0, so input 0 means we go to 1, 0 and output is also 0. So next state is 1, 0. Okay, and we have input as 0. So input 0 means we go to 0, 0 and output is 0. So we are at 0, 0. Okay, and now our input is what? It is 1. So input 1 means we go to 0, 1 and our output is 0. So 0, 1. Okay, and now input is 1. So 0, 1, input is 1. So we go to, means we stay at 0, 1 only and output is 0. Have I done some mistake or what? No, this is correct. So 0, 1. So we are at 0, 1 and input is 0. So output is 0 and we move to 1, 0. So this is 1, 0 and over here input is 1. So output is also 1 and we go to 1, 1. But I am getting 3 as your answer. Why? Have I skipped some one at any place? Look. So this is one place. Fine. This is another. This is one more. So 4 is the correct answer, but I guess somewhere I have skipped 1, 1. So when are we getting from 1, 0? So where are the places where we get 1, 0? So here we get 1, 0. 1, 0, 1, 0. Any other place we have 1, 0? No. So where is one more 1, 0 we should be getting? So 4 you guys are getting, but I am getting 3. So I have done mistake, I know. So where it is, I am trying to find out. Okay. So tell me at which position? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. At which clock pulse I have made a mistake? 0, 0, 0, 1. At fifth position, present state is 0, 1. Input is 1. Output is 0. We should be at 0, 1. No, at fifth position, input is 1. Present state is 0, 1. Okay. So next state should be when input is 1, that means it will remain at 0, 1 only. So output will be 0. 1, 2, 3, 4, 5. So what? What in the output I am not getting, Shruti? At the fifth position. Okay, we will do it once more. See, when your present input is 0, 0, means I have written all the inputs over here, everything is written. So you can see when present input is 0, 0, input is 1. So I go to 0, 1, and your output is what? It is 0. So now your next state is 0, 1. So this is 0, 1. Input is 0. So input 0 means you go to 1, 0. Your output is 0. Okay. So now you are at 1, 0. So such kind of question you need to be mentally very much prepared for solving. So even at one place, if you mess up, you are going to mess up the entire question. So that is why we won't be solving it with such method. Okay. We won't be solving it using this method. This is the analytical method. So look, we are at 1, 0. We apply input 1. So output is 1 and we go to 1, 1. So now we are at 1, 1 and we apply input 0. So we go to 1, 0. Output is 0. So now we are at 1, 0. Input is 1. So when 1, 0 input is 1 means we are again going to 1, 1. Okay. We are again going to 1, 1. You can see it is 1, 0. I am applying input 1. So output is 1 and we are going to 1, 1. So 1, 2, 3, 4, 5. Yes, you are correct. So somewhere over here, Shruti, it should have been 1. So yes, I messed up at this position. Okay. So now this will be what? This is 1, 1. If you have input 1, so you will go to 0, 1 and your output will be what? Output will be 0. So 0, 1. Input is 1. Input is 0. So you will go to 1, 0 and output is 0. Now again we are at 1, 0. We are input is 1. So again I will go to. So I will means input is 1. We are at 1, 0. So we will go to 1, 1 and output will be 1. So this is again 1, 1. So 1, 1, if input is 1, we go to 0, 1. Okay. So 0, 1, input is 0. So we go to 1, 0, output is 0. So again 1, 0, we go to 1, 1. Now this time I am getting some more ones. What is happening here? So 1, 0, input is 1. Where am I messing it up? Okay, let us see. So 1, 1 we have. So if it is 1, 1, we will again go to 0, 1. Output is 0. So 0, 1. Output is 0. So we go to 1, 0. Output is 0. Once again we have 1, 0 and input is 1. So I have messed up once again. Now we are getting 1, 2, 3, 4, 5. 5 ones. What is happening? This is not at all the correct way of solving. What is happening? So at this point, once again, I am messing up. This is 1, 1. Okay, 1, 1. So present input is 1, 1. Again, let us check from here. So if this is 1, 1, so where was I? Over here. So if input is 1, so we go to 0, 1, output is 0. Okay, 0, 1. Now input is 1, input is 0. So we go to 1, 0, output is 0. So 1, 0, input once again it is 1. So we move to 1, 1, output is 1. So once again we have 1, 1 and input is 0. So we go to 1, 0, output is 0. So this is 1, 0. So it is 0. So once again we go to 0, 0, output is 0. So 0, 0, we are at this state, input is 1. So we go to 0, 1, output is 0. We are at 0, 1. Okay, 0, 1, input is 1. So input once 1 means we will stay at this state only. So this will be 0, 1, output is 0. So 0, 1. Now once again we are at what? At this state, so it is 0. So where shall we move? We shall go to 1, 0 and output is 0. Now it is 1, 0. We have input 1. So we go to 1, 1 and output is 1. So now you can see this is correct. We have 1, 2, 3 and 4 ones. Okay. So after this much time, even I am able to get your answer is 4. Okay. So this was the analytical way of solving this question. So very quickly note this down. Very quickly note it down. So after this, I will show you the very shortcut trick with the help of which we are going to solve. Okay. So this is not the way we will be solving such kind of questions. See, you have your input sequence. Okay, you have your input sequence. So what is given? The state diagram of a finite state machine FSM designed to detect an overlapping sequence of 3-bit. Overlapping sequence means what? That basically there is some sequence, we don't know. The sequence can be anything. It can be 0, 0, 0. It can be 0, 1, 0. Okay, it can be 1, 0, 1. Any sequence of 3-bit, it is possible and you have to detect it. So basically this is your overlapping kind of your sequence detector. So in the first clock pulse, it will check this first 3-bit. Okay, suppose that this bit is being detected. So in the first clock pulse, it will check the first 3-bit. So you can see that this is actually matching with this one. So output will be 1. Okay, fine. So in the second clock pulse, as this is your overlapping bits, means overlapping sequence detector. So in the second clock pulse, it will start to check from here once again. You can see this is different from here. So this will produce 0. Like this will go on till the last bit. Okay, till the last bit, this will go on. So now first we have to basically detect what is the input sequence that is being checked over here. Okay, first we need to check the input sequence. So for that, look in the state diagram. Okay, that what is the input sequence. So you need to see that from where to where you are going. So first look, when you are starting from where? The initial state of FSM is S0. So you are starting from this position. So where do you get your 1? You get 1 at this position. So now look what you have to do in this finite state machine. Start from your initial position. What is your input? So if you see over here that your input at this place is what? It is means you are at this state 0 0. Okay, you are at this position. Now if you apply input as 0, listen very carefully, afterwards you can note. See, if you apply input 0, you are staying at the same place. Don't care about the output at the moment. Just think that if you apply your input 0, you are staying at the same state. So this is unnecessary. Okay, this is not required, because as you are counting sequence, so you need to move into some other kind of state for counting. So if you stay at your same state only, then how are you going to count? So that means you need to proceed to some other state. So for what input are you going to next state? So if you apply input 1, then you are going where? You are going to 0 1. So the first bit of your sequence detector is 1. If you get 1, you will go to some other state, remember, and that state will be 0 1. Fine. Now check over here. If you apply input 1, at the moment I am telling you guys to ignore the output. See, if at this place you apply input as 1, you will be staying at the same state. Look over here, if input is 1, you are staying at same state. So this is not required. You need to move to the next state, because you want to count the sequences over here. So when can you go that? If your input is 0, so you will move to the next state, that is what? 1 0. So the next bit of your counting sequence is 0. Okay, it is 0. Why? Because when you give 0, you go from 0 1 to 1 0 state. Okay, fine. So now when you are at 1 0, you can see what? If you apply input 0, you are going to S0. Okay, if you apply input 0, you are going to S0, that is 0 0. Now some of you might say, sir, that we are going to some other state only, so let us give 0 over here in the sequence detector. But this is not the case. At this very time, you need to look where? You need to look at your output also. Okay, at this moment you need to see your output. Why? Because when you apply input 0, your output is 0, and you are moving to some previous state that has been already covered. But when you apply input as 1, so what you get? When you give input as 1, you can see you are going to some different state which has not been covered yet, that is 1 1, and now you get your output 1 for the first time. So the place where you get output for the first time, you will be terminating your sequence, that sequence will be getting detected. So after 0, you can see I am proceeding to the next state when my input is 1. And you can see for this one, my output is 1 for the first time. So you have actually detected the sequence. So this is your sequence that is being detected. So tell me, is this clear to you guys? How to get this? Tell me, is this clear? Any doubts that how I am able to determine this sequence? Now see, now this is very simple. Okay, it is very simple to solve. So we have this as what? So basically this is your overlapping sequence. So whenever you have overlapping sequence, it is actually advisable that you check it like this. First you put one arrow, means over here what I will be doing, it will be very simple for me. So I will be marking something like this. Okay, I will be taking something like this, and I will be translating it. So you can see I will count on my fingers. Okay, I will count on my fingers that what is the sequence. So you can see this sequence is matching. So for the first clock pulse only I will be getting 1. So now you can see this is for the next 3. for the next 3 bit. So this is not matching with this one, so this will be 0. Again you can see this is 101, so one more 1 will be generated, output will be 1. So 2 times I already have 1. Now next you can see it is 011, next is 110, so this is not the sequence. Again you see 101, so this is my sequence, so I will be getting third time 1. So again you can see this is 010, 100, 001, 011, 110, and the last once again you are getting 101. So in total you are getting 4 ones. Okay, 4 times 1 you are getting. Okay, 4 times 1. So it is very easy for me over here to count like this, but if in exam you are given with such question, so what you will do, once you will put over here. Okay, you can see it is 1, so write 1 over here. Next time you put over here, so you can see this is not the sequence. Next time you put over here, you can see again this is the sequence, so write 1. Next time you put from here, so this is not the sequence. Again you put from here, so this is not the sequence. Again from here you can see this is the sequence. Again from 001, 010, so this is not the sequence. This is 100, not the sequence. 001, not the sequence. 011, not the sequence. 110, not the sequence, and the last time you have is 101, so one more time you have 1. So these are 4 times 1, you can see. So like this you can solve the question of sequence detector. So this was overlapping sequence, that is why I have counted like this. But if this was not overlapping sequence, then how would I have counted? So simple, in the first time I will consider this 3 bits, so this will produce 1. If this was not overlapping sequence, so the next time you can see this is 0110, so this will be 0. Next time this will be again 0. See, if you don't have any bits over here, you can add 0 at this position. So you can see this will be again 0. So this is only one time you will be getting your output 1 when it is non-overlapping sequence detector. Is this question clear? So this is the way you are going to solve this in your examination. Okay. This is the proper approach with the help of which you are going to solve your questions of sequence detector in your exam. Any doubts? Doubts, anyone? Okay, fine. So what I will do, I will frame one question myself of sequence detector and I will give it to you in the next class. Okay. So homework I will send you, because first I wanted to discuss this method and then I wanted to give you one question. So I will give you one question in the next class. Okay. Regarding this overlapping method. Okay. So in the last class I had given you this. Okay. I had given this question. So tell me now, what is JA, KA? We had derived JA, KA. So we have JB, KB and we have JC, KC. So tell me if these were correct or not. This JB, KB, JA, KA. So are all of them correct? So we had actually derived this. Okay. We had derived all of them. JA, KA, JB, KB, JC, KC. Okay. So is everything correct over here? Means you only have derived this. Okay, fine. So if everything is correct, so now I had given some more thing over here. Check if it is a self-starting counter and also find the number of residual clock pulse. Now what is this basically? So for that, first let us write the next state equation of flip-flop A. Okay, so next state equation will be what? An plus 1 is equal to JA an complement plus Ka complement an. So we have already derived Ja. So Ja was what? It was Bn. An complement plus Ka was what? It was Cn. So Cn complement An. Okay. Ka was Cn. Now I don't think K will be Cn over here. Can anyone check what is Ka? Means you guys had told me that Ka is Cn. Can anyone check what is Ka? I don't think it will be Cn. 0, 1, 2, 3. 6, 7. So this will be Bn. It is not Cn. Okay. So Ja is also Bn, Ka is also Bn. Now this will be also Bn complement. So you can see this is An XOR Bn. Okay, An plus 1. Okay, so next is what? Next state equation of flip-flop B. Okay, next state equation of flip-flop B. So that will be Bn plus 1 is equal to Jb Bn complement plus Kb complement Bn. Okay. So what is JB? JB we have An complement plus Cn into Bn complement plus Kb was what? Kb is 1. So that will be 0. So no need for writing because it is 1. So 1 complement will be 0. So this will be what? An complement Bn complement plus Bn complement Cn. Okay. So this will be what? This will be Bn plus 1. Now let us write your next state equation of flip-flop C. Okay. So that will be Cn plus 1 is equal to Jc Bn, Cn complement plus Kc complement Cn. So what was Jc? Jc was An, Kc was Bn. So An Cn complement plus Bn complement Cn. Okay, Bn complement Cn. So now we have the next state equation of An plus 1, Bn plus 1, Cn plus 1. Now one more task I am giving you. Please don't get angry on me. So this is very simple. What I want you guys to do is just calculate me the next state very quickly. Okay. So then I will tell you what is residual clock pulse and self-starting counter. So tell me very quickly with the help of next state equation. So such kind of question means like this is a total subjective question. Okay. So this was asked in your engineering services. Okay. Mains examination. So such kind of question will not be asked in GATE, but some of the concept might be asked, like what is residual clock pulse, okay, if it is a self-starting counter or not. All those things will be asked. So very quickly tell me what will be your next state over here. Okay. So I know from 0 it will go to 2. That I know because it has already been given in the question. From 0 to 2, 2 to 4, 4 to 5, 5 to 7. So all these states I know. From 0 it will go to 2. Okay. From 2 it will go to 4. So from 2 it will go to 4. Okay. And from 4, 5, 7. Okay. From 4 to 5 and from 5 to 7. So all the states I know. You have to calculate the remaining states where it is going. So I have given you the next state equations. Okay. So tell me. So when it is 1, where is it going? So 1 means 0, 0, 1. Okay. 0, 0. So this will be 0. This will be A and B, and so this will be 1. Okay, so Cn is, so this will be 0, 0. So this will be 1. So it will go to 3. What about this one? So this will be again from 4, means this is what? This is 3. So from 3, this will be 1. Over here, this is what? Bn complement 0, Bn. Okay, so this will be 0. Over here, this is 0, Bn 0. So this will go to 4. And last is what? Okay, so we have 6 and 7 also. Okay, from 7 it was going to 0 back. Okay, so I don't need to calculate. So from 7 again back to 0, I need to calculate for 6 only. So for 6, if I have to calculate, 6 is 110. So this will be 0. Over here, this is 0, 0 from 6. And this will be an 0. So 1 0. Okay, so this will be 1. So 0 1 1. Okay, fine. Tell me if you are getting this or not. Are you people getting this? Is this clear? See, in this table, in this state diagram, we were missing the states. See, basically it was designed using a 3-bit, means 3-bit, it is a 3-bit, and we have designed it using 3 JK flip-flops. So out of that, you can see state 1, state 3, state 6. All the states were missing. We had no information if our counter was going in this state, then what will be its next state? We never knew. But now we have information of that also. We can draw the complete state diagram. So look, when we are at 0, we are going to 3. Okay, we are going to 3. When we are at 3, we are going to 4. Okay, when we are at 4, we are going to 5. When we are at 5, we are going to 7. And when we are at 7, we are going to 0. Fine. But now what happens if we are at 1? So if our counter, suppose if our counter it goes to 1. 1 means what? That it is 0, 0, 1. Okay, if our counter is in this state, so what will be its next state? It will go to 3. Okay, fine. So now if our counter is in your 1, suppose it is, sorry, I had taken 1. So 1 will go to 3. Wait a second. So 0 was going to 2. Sorry. This was 2. From 2 to 4. Now it's correct. So I have drawn one mistake over here. So from 1, we are going to 3. Okay. So from 3, we are going to 4. Okay. So there was one more missing state. It was 6. So when we are at 6, we are going to 1. So if by chance our counter, it starts at 6 or it starts at 1 or at 3, you can see even then it will go into counting state. So the 6, 1, 3, these are all unused state. But even if we initialize our this counter, okay, if we initialize this counter that has this next state equation, even from one of the unused state like 6, 1 or 3, we are going into your use state. So such kind of counter where we go from unused state to use state, such kind of counter is known as your self-starting counter. Why self-starting? even if we keep the counter in one of the unused state, our counter is going into use state. So this is your self-starting counter. And residual clock pulse, what do we mean by residual clock pulse? So residual clock pulse is the maximum clock pulse that is required for your counter to go from unused state to used state. So maximum number of clock pulse for going from unused to used state. So you can see if we start from 6, so this will take 1 clock pulse. From 1 to 3, second clock pulse. From 3 to 4, this will be 3 clock pulse. So after 4, you can see your counter will be in your use state. Continuously it will go on and on in the state. So your residual clock pulse over here, residual clock is 3 TCLK, where TCLK is what? It is your time period of one clock cycle. Tell me if this concept is clear or not. What is self-starting counter? What is residual clock pulse? Is this clear? Is this clear? So in exam, they won't be asking you like this. They will give you one counter. Okay, they will draw one diagram. Okay, one synchronous counter. And they will ask you whether it is your self-starting counter or not. So you need to do what? By looking at your counter diagram, you have to calculate all the next state equation. Then you have to construct the complete state table. And with the help of state table, you have to see whether your counter it is going from any of the unused state into used state, then you will say it is self-starting counter. And if they ask residual clock pulse, so for residual clock pulse you need to search for maximum clock that your counter is taking from going from your unused state to used state. Tell me if this is clear or not. Is this clear, everyone? Any doubts? Any doubt, anyone? Okay, fine. So then, since you guys are not responding, any issue? Tell me. Anything you want to ask?
Hello.
Yes, tell me.
In that table, from 4 to 4, I guess it is not 4 to 5, but how in state diagram it is going 4 to 5?
Oh, look over here. From 4 it is going to 5. I have done a wrong over here. So this should have been 5. Okay. So
Okay.
already we knew this state. And even if you put in this, even if you put over here, so you will get 5 as your answer. So directly I put all the state because this was given in the question. With the help of this only we constructed this this next state equation. Okay. So I knew about all the state because this was given in the question, but I never knew if our counter was ever in your 1, 3 or 6, what would be the next counting sequence. Okay. So for that only I had done all this thing. Did you understand now?
Yes.
Okay. So next is what? Next we have is your flip flop. Okay. So means flip flop we are studying, but there are some triggering techniques that we need to talk about. So flip flop, okay, flip flop, basically it is of two types. Okay, two types means, sorry. So two type means what? Either it will be level triggered or will be edge triggered. Okay. So what do we mean by level triggered and edge triggered? So level triggered of the clock or edge triggered of the clock. So usually we represent your ideal clock cycle, clock pulse like this, a square wave, okay, a symmetrical square wave, but it looks something like this. Practically, it looks like this. Okay, it will look like this. So we are not, means we are not going to study microprocessors. So tell me, how many of you are from EC, electronics and communication? At least we can say this, that sir, we are from EC. Only one, Shruti, no one else. Okay, so means even you have to read computer architecture. Previously, this chapter, microprocessor and microcontroller, was there for EC, but now it has been removed from 2020. Means only for instrumentation student they have microprocessor. So when you have microprocessor, you might be seeing that practical clock, but in this course we will always have what? We will have this ideal square wave or ideal clock pulses. So in this, what is this positive level? What is this negative level? So if your flip flop is level triggered, okay, so then what will happen? Your flip flop is allowed to change state. If it is your positive level, it is allowed to change states only at this level. If it is what? If it is your positive level triggered flip flop, at this state, this is also one positive level. Okay. So your flip flop is allowed to change state only at this positive level. While at this negative level, your flip flop will hold the state of this positive level. When it is at this negative level, if it is a positive level triggered flip flop, then at this negative level, it will hold the value of this positive level. Okay. So this is what? This is your positive level. Similarly, if it is negative level triggered, so these are all your negative levels. So at this places only your flip flop is allowed to change states. Okay. So this is what? This is your negative level. Negative level. Now these are your levels. Now if suppose our flip flop is edge triggered. So edge trigger means what? Edge means at the instant or the moment. Okay, momentarily. So that is known as what? That is known as your edge. So for edge triggered, we have positive edge and negative edge. So we get a positive edge when your signal goes from low to high. So we will get what? We will get your positive edge. And when your signal goes from high to low, we get negative edge. Okay. So positive edge, when we go from low to high. At that time, we will encounter one positive edge. When we go from high to low, we will be getting what? We will be getting your negative edge. So over here, you can see we are going from low to high. So this will be your positive edge. Similarly, once again, you can see you are going from low to high. So this will be also one positive edge. Now, what about negative edges? So you can see over here that you are going from high to low. So this is one negative edge and this is one negative edge. Okay. So these are your positive edges and negative edges. Now, if you ask me, sir, if it is your edge triggered, so can a flip flop change in this much momentary state? Yes, it can change your state in this very moment. Why? Because even if your input has changed, suppose your flip flop input has been changed at this moment, okay, at this moment, at this negative level, but it will actually do what? It will not change its value in this moment. It will change only its output when it encounters this edge. And after this edge, immediately after this edge, whatever is the output, it is going to be holded for this entire duration until your positive edge triggered flip flop, it encounters the next positive edge. So that will be encountered over here. So until this point, from here to here, your flip flop is going to hold the output, whatever your output was after this edge. Okay, whatever your output was after this edge, it is going to hold that value up till this edge. Similarly for negative edge also, it will change your output at this edge, and then it will wait till your next edge for your output to make a transition if there is change in input. Tell me if this is clear or not.
So I didn't get that.
What you didn't get? See,
Uh,
basically clock are used for synchronization. Okay, clock are, Shubham, where were you? Means class started from 8:30 and you came just now.
I was fixing my laptop because I was not able to hear you.
Okay, it's okay. So I was telling, basically, see, what do we mean by synchronization or triggering? So synchronization means what? That all the flip-flop in the circuit, they should actually give output at the same moment. Okay. So you can see, basically, if our flip-flop, if suppose it is your positive edge, so positive edge means what? That your flip-flop is allowed to make transition in your output. So when will your flip-flop output transit? When there is a change in input. If input changes, then only output changes. So if assume your input of a flip-flop, of a positive edge triggered flip-flop, listen very carefully. If suppose for a positive edge triggered flip-flop, your input changes at this moment, okay? At this moment it changes. But output will not change for a positive edge triggered flip-flop till the point where your flip-flop doesn't encounter your positive edge. If suppose your flip-flop encounters a positive edge at this point, then it will change its input if this input has been held constant from this time to this time. If it is held constant, then this edge triggered, positive edge triggered flip flop is allowed to change its output at this moment. But after this moment, after this precise moment, your output will be holded until the next positive edge. Okay, until the next positive edge. So basically your flip flop, it will change states only when it encounters a positive edge. If it is a positive edge triggered flip flop, it will change its output at negative edges if it is a negative edge triggered flip flop, or it will change only in the positive level if it is a positive level triggered. Similarly in the negative level if it is a negative level triggered flip flop. Tell me now if it is clear. Is this clear, everyone? Shubham, is it
Yes,
clear to you?
yes.
Okay, so even if it is not clear, we will try to understand it with the help of one example. If suppose we have a clock over here, okay, this is your clock. So I haven't written over here whether this is your positive edge, negative edge, triggered flip-flop, what it is. I haven't told over here. Okay, fine. So now if suppose I take a random input, okay, I am taking a random input that I will be giving to a D flip-flop. Okay, so this is your D flip-flop. So I haven't told whether this is clock, means clock is edge triggered or level triggered. So I won't be writing this. So let me write it like this. Okay. So this is clock. I haven't told you whether this is positive edge or negative edge. So if it is your positive edge, then clock will look like this for positive edge. For negative edge, there will be a bubble. Okay. For a negative edge, there will be a bubble. If it is level triggered, then this triangle, it will not be present. So this will be negative level. If for positive level, this triangle will not be present, this will be positive level triggered flip-flop. So this triangle is going to be present for your edges, and if there is a bubble, then that means a negative edge triggered. Okay. So now let me give, this is your D flip-flop. I am giving input to it. We know output will be what? Output will be equal to your input in your D flip-flop. We know this. Okay. So note it down very quickly, this one. Note this till the time I generate one input, random input. So this is input to D flip-flop, D in. Okay, D in. Now assume in the first case, this D flip-flop is what? It is positive level triggered flip-flop. Okay, positive level triggered. So for positive level, we know what? This flip-flop will only allowed to change state at your positive level. So I will not be messing up the diagram. Just once I will mark. So these are your positive levels only at this position. First see, then you can copy. Okay, I will give you 1 minute to copy. But first look over here and understand. So these are your positive level. Only at this places your output is allowed to change according to the change in input. Okay. So look over here, this is positive level. So this is negative level. So in negative level, let me assume that I have initialized the D flip-flop from 0. So look over here. At this point, the flip-flop senses that this is your positive level. Okay. If it is positive level, then this flip-flop is allowed to make changes in the output. But what is the input? Input is still 0. It is 0, 0, 0. At this precise moment, you can see that your output is going where? It is going from 0 to 1, and this is lying in this positive level. Nobody is going to copy. First understand, then you can copy. So you can see there is a change in input in this positive level. So immediately your output will change. Why? Because this is positive level. And you can see in this positive level, it is staying at 1. So output will be at 1 till the next positive cycle, till it encounters the next positive cycle. It is not due to the fact that this input is not changing. If suppose here input was changing something like this, so that is why I told you not to copy, because I will be changing the diagram. If suppose your input was changing like this, but still your output won't be changing, because the last input that your D flip-flop it got at the end of this positive level clock was that your input was high, so output should be maintained at high. Even when there is a transition in input from high to low and low to high, your D flip-flop it did not change, because this transition happened in your negative level, so your output will not change. So immediately at this positive level, you can see output is changing at this point. Sorry, input is changing at this point, so output will change. Now in the next positive level, you can see this is 0, so this will continue. Again, you can see in this negative level, out input is changing, but this is a positive level triggered flip-flop, so it will maintain its state that has been over here, so 0. Now look, at the starting of this positive level, output is 1. So immediately your D flip-flop will switch to higher state and it will stay over here until this point. There is a change in input from high to low in your positive level. So you are going to come back over here once again and you are going to continue with this state. You can see in the next positive level also it is 0. So that is why this will be 0. In the negative level, there is transition. So we are going to stay at 0. But look over here. At the next positive level, this is staying, means this is going to 1. Why? Because you can see your input is high. So immediately it will go to 1 and it will stay over here like this. Okay. So it will continue. So tell me, any doubts in this? Doubts? Anyone? So if there is no doubt, now you can note for this positive level quickly. See, if there is doubt, you can ask me. Note it quickly. So I want you guys to do what? Please draw the negative level. For negative level, those of you who have completed noting, so use a pencil to draw for the negative level, so that if you are wrong, then you are able to erase it. Okay, so use a pencil and draw for the negative level in the same diagram. So your diagram should look like this only. See, if you make proper notes, then it will be easier for you to understand also later on. See, for negative level, you can see this is your negative edges. This is your negative edge, negative edge, negative edge, negative edge, negative edge, negative edge, negative edge. Okay. So in the negative edges, you can see your input is what? It is 0. Fine. So it is 0. Now here it is positive edge. So in the positive edge, what was the last value in the negative state? That will be holded in the negative edge. Now immediately when you encounter this negative level, you can see input is high. So immediately this output will go to high. And there is a transition from high to low and back again to high in this negative level only. So same input pattern is going to be followed. Why? Because this is D flip-flop and I have assumed BRB. Arey, where are you going, Bhumika? Okay, so you can see what? That this transition or whatever change in input, it is happening in your D flip-flop and it is happening in your negative level triggered D flip-flop. And on top of that, your D flip-flop, it has zero propagation delay. So at the moment, I am not talking about propagation delay anywhere. Later on, we are going to study propagation delay in flip-flop. But at the moment, I am assuming that whenever there is a change in input, immediately your output will change in your flip-flops. So you can see in this negative level, your input is being maintained to 1. So in the next whole positive level, it will be continued to 1. But in the next negative level, this negative level, don't copy. Later on, you can copy. So in this negative level, you can see your input is 0. So immediately it will go to 0 and stay over there till your next negative edge, next negative level. So in this next negative level, you can see there is a transition from 0 to 1 or low to high. So immediately your flip-flop will also change from low to high and it will continue its state. See, till here. This input had changed before this time only, but your output, it does not changes till the next negative level. At the next negative level, it will go to 0 and it will continue till the next negative level, where once again it is seeing that there is a transition from low to high. So your output for a negative level, it will look something like this. Tell me if this is clear or not. Is this clear? Everyone tell me. At least respond, okay? Please respond with me. If you don't respond, I will not be knowing that whether you know or not. And then you will be complaining that, sir, we are not able to understand. So please tell me if you are understanding, it's okay. If you are not understanding, then let me know. So copy it down very quickly. Okay, so next what we have? We have, if suppose a positive edge triggered D flip-flop, okay? A positive edge triggered D flip-flop. So positive edges, where do we have? So this is your positive edges. Only at the positive edges your flip-flop is allowed to change. So this is the most important one. So you can see over here that at this positive edge, D input is 0. So this is going to 0 till the next positive edge. So at the next positive edge, input is 1. So immediately output of your flip-flop will go to 1 until the next positive edge. At the next positive edge, you can see input is 0. So immediately this will go to 0 and this value will be holded till the next positive edge. So at next positive edge, you can see input is 1. So output will go to 1 and it will be holded till the next positive edge. So at the next positive edge, it is 0. So immediately again it will go to 0 till the next positive edge. At the next positive edge, again it is 1. So this is going to stay at 1. At the next positive edge, you can see your input is high. So output is also going to be high only. So this will be for positive edge. So tell me, is this clear? Is this clear, everyone? Any doubt in this? Now last is what? We have your negative edges. So for negative edges, these are your negative edges. Okay, these are your negative edges. So your output is only allowed to make transition in your negative edge. This is negative edge. So look, initially at this negative edge, input is 1. So initially it is 0. So at this point, you can see input is 1. So till your next negative edge, your output is going to be holded at 1. So look, what is the value of input over here? It is 0. So this will go to 0 and stay over here till the next negative edge. At the next negative edge, again it is 0. So it will stay at 0 till the next negative edge. Again at the next negative edge, you can see it is 0. Input is 0. So this will stay at 0 only. Again at next negative edge, it is 0. So it will stay at 0. At this negative edge, input is 1. So output will immediately go to 1 and it will stay at 1 till the next negative edge. At the next negative edge, it is 1. So it will continue at 1. So these are the output of positive level, positive edge, negative edge for this input. Is this clear, everyone? Tell me. Any doubts? Bhumika, Chandana, Piyush, Raju, Shubham, Shruti. Okay, fine. So now let us study the concept of asynchronous counter. So in asynchronous counter, basically the clock that we have, so we don't give the same clock to all the flip-flops. Okay. So let us assume that this is your negative edge triggered flip-flop. Okay. Negative edge triggered JK flip-flop and your asynchronous counter. Remember this, if it is your asynchronous counter, either it will work in your J is equal to K equal to 1, that is in toggle mode, or if it is your toggle flip-flop, it will be 1. So synchronous counter always works in your toggle mode. Okay, it doesn't work on any other mode or any other flip-flop. If it is your JK flip-flop, it will work only when J is equal to K equal to 1. And if it is your toggle flip-flop, then it will work when T is equal to 1. Okay, so asynchronous counter, it only works with your JK flip-flop in toggle mode or in toggle flip-flop when T is equal to 1. Okay, so now what I told you that this is one negative edge triggered flip-flop. So how will its output look? So I have told you that input is going to be 1 1. So we know what, whenever J and K equal to 1 1, so next state will be what? So if J is equal to 1, so this will be Q complement plus this will be 0 dot Q. So Q plus is equal to Q complement, and we know what, that this is your toggle mode. So whenever JK equal to 1, it will work in your toggle mode. Okay. So let us draw the clock. So I am telling that this is what? This is your negative edge. Okay. So this line is not required. Okay. So this is your clock pulse. Let us mark the negative edges. So these are your negative edges. Okay. Okay. So these are your negative edges. Let us assume what? That initially the state of flip-flop is 0. So it is working in toggle mode. So initially the state of flip-flop is 0. So the moment we encounter one negative edge, basically the flip-flop will toggle its state. So it will toggle from 0 to 1 and it will stay at this state till the next clock pulse. So at the next clock pulse, it will toggle from 1 to 0 and again stay at 0 till the next clock pulse, means next clock edge. And at the next clock edge, once again, this will go to your 1. So this is what? 0, 1, 0, 1. So this is a 1-bit asynchronous counter. And you can see it is counting from 0 to 1 and again from 1 to 0. And we know what? For a 1 means for a 1 flip flop, basically the number of states are how many? 2 to the power 1. So that is 2. So you can see over here that we have 2 states. Okay. Not Chetan Bhagat's 2 states. Okay. So this is the 2 states of binary. Okay. So 2 states over here we have. So note it down very quickly. Note it down. So this is your first clock. This is your first clock. This is your second clock pulse. This is your third clock pulse. Okay. Or you can even assume this to be as, means I have told you that we have initialized the clock. So let us assume this is the 0th clock pulse, because I told you I have initialized the counter from 0. So this was the initial state. So initial state at 0. At the first clock pulse or first clock edge, it is going to change its state. And this is your second clock pulse. And they keep on continuing. Okay. Is this clear? Note it down quickly and let me know. Now, if you had, means this output was taken from Q. If you had taken output from Q complement, then it would have been like this. Okay. Then it will be like this. It will be 1, 0, 1, 0. Just the opposite of this one. If you had taken output from Q complement. So then it will be 1, 0, then again back to 1. Okay, so 1, 0, 1, 0 like this. Okay, fine. So next we have is what? Next we have is a 2-bit asynchronous counter. Okay, 2-bit asynchronous counter. So very quickly first draw the diagram. So once again you can see I have kept this JK flip-flop in your toggle mode and I am telling what? This is QA, this is QB, means this is A flip-flop, so this will be JAKA, this is B flip-flop, so this will be JBKB. Okay, fine. So at the moment, okay, let me ask you this question later on. First, let us draw the clock pulses. So this is also negative edge. You can take positive edge also. Okay, you can take positive edge. It's up to you. But here I am taking negative edges. Okay, so these are my clock pulse. Okay, if you have not noted, so you can note down later. First, look over here. So these are all negative edge triggered. So these are my negative edges of the clock pulses. You can see. So this is what, this is my clock. So I will give you time to note. Okay, I will give you time to note. Am I audible properly? Am I audible? Tell me yes or no, because there was net sign over here at my tablet. Okay, so look over here. So this flip-flop, let me first draw output QA. So let us assume initially QA is equal to 0 and QB equal to 0. So this is your 0th clock pulse. This is your first clock pulse, second clock pulse, third clock pulse, fourth clock pulse, fifth, sixth, and seventh. So initially QA, QB is 0. Okay. So if it is 0, so initially QA is at 0. So basically this JK flip-flop is working in your toggle mode. So if this is 0, so immediately at the encounter of the first clock edge, it will go to 1 and then it will start toggling like we have seen. So you can see there is toggling continuously from 0 to 1, 1 to 0. Now you can see what? That basically this QA, look in this diagram, this QA is being given as the clock. A negative edge of this QA is acting as your trigger for this B flip-flop. Look over here. This QA is basically, its negative edge is acting as your trigger for this B flip-flop. So mark all the negative edges of this QA. They will be actually acting as your trigger or clock edges for your B flip-flop. So okay, so let me now start with QB. So QB is also starting from 0. So you can see this will be in 0 till the first active edge. Active edge means what? The negative edge of this QA. And at that precise moment, it will change to from 0 to 1. Then again from 1 to 0 at the next negative edge of QA. And this will keep on going like this. So you have what? 0, 0, 1, 1, 0, 0, 1, 1, 0. So you can see we have QB, QA. Now if suppose, basically this is a 2-bit counter. Can you tell me what will be the order? Will it be QB, QA or will it be QA, QB? Option 1 or option 2? Along with Y. Why you are saying so? So option first or option second, which one do you think will be the order of counting? QB, QA. Why so? So look over here. We know if this is AB, so your LSB, it toggles the most. Okay, you can see it is toggling the most, whereas your MSB toggles the least. So this is for a 2-bit. Similarly, if we have 3-bit, so this will be 0, 0, 0, 0. This will be 1, 1, 1. This is 0, 0, 1, 1, 0, 0, 1, 1. And this is 0, 1, 0, 1, 0, 1, 0, 1. So if all the states are of one clock, okay, transition is taking at 1 clock. So you can see this is MSB. MSB is transitioning after 4 clock, whereas LSB is transitioning at each of the clock pulse. After each clock pulse, it is making one transition. So LSB toggles the most, whereas MSB toggles the least. So in this case, where do you see the toggling is happening the most? Toggling is happening more in your QA and least in QB. So that is why QB is your MSB, whereas QA is LSB. And one more trick is that the flip-flop where we apply the external clock, that is LSB, and the flip-flop that is farthest from the external clock, it is MSB. So this is the flip-flop that is farthest from your external clock. So this is your MSB. Okay, so what I said, the flip-flop that is connected to the external clock, it is LSB, and the flip-flop that is farthest from the external clock is your LSB. So your counting sequence will be what? It will be 0 0. So in each of the clock pulse, it will be counting. Counter will be counting. So this will be 0 0. This will be 0 1. This will be 1 0. Over here, this will be 1 1. Again, you can see 0 0, 0 1, 1 0, 1 1. Again 0 0. So this counting sequence will go on and on. Okay. So if I take output from here, if I take output QB QA, my counting sequence will be what? So have you noted this down? So note this down. So if you take your output from QB QA, your counting sequence is 0 0, from 0 0 to 0 1, from 0 1 to 1, from 1 0 to 1 1, and then again back to 0 0. So this is basically mod 4 up counter. Why so? Because you can see there are 4 U state over here. Okay, 4 U state. So that is why mod 4, and it is up counting from 0, means in ascending order, 0 1 2 3, then again back to 0. But if you take output from QB complement QA like this, that is from here, if you take your outputs, then what will you get? Simply the reverse state, means the complemented state. So the complemented state of 0 0 will be what? It will be 1 1. This will be 0 1 will be 1 0. Next will be 0 1. Last will be 0 0. And again from 0 0 to 1 1. So this is mod 4 down counter. Tell me if this is clear or not. This is mod 4 down counter. Very quickly note this down. Note it. Okay, one more thing I want to share. If suppose the time period of this clock is TCLK and the corresponding frequency is FCLK. So we know what? FCLK is equal to 1 by TCLK. Okay, so this is in Hertz. So if this is what? If this is TCLK, so you can see what? That basically the time period of QA is what? It is 2CLK. So time period of QA is equal to 2 TCLK. So frequency of A will be what? It will be F clock by 2, because time period is doubling. So frequency will go half. Tell me if this is clear or not. And over here you can see that basically time period of this is what? It is 4 clock, means 4 TCLK. So time period of QB is equal to 4 CLK. So that is why frequency of B, it will be f clock by 4. Okay, this will be what? It will be f clock by 4, or it will be fa by 2. So whichever you want to write, fa is basically what? It is the frequency of qa. So note it down very quickly. A lot of information I have written. So note it down very quickly. I will wait 1 minute for you guys. I will wait 1 minute. Noted? Okay. So now let us move to the next topic. So over here means I have once again taken negative edges. So let us take positive edges, because till now we have solved 2 questions of negative edges. So let us see for positive edge what we get. So let us assume, okay, JB I have written. So this is 1 1 1 1 1 1. Okay. So let me draw. Okay. So already I have drawn over here. So let me try to take the clock from here. So very quickly you draw the diagram till the time I also make changes over here. So very quickly draw the diagram. Okay. So now I have told you that all the flip-flop are positive edge triggered. Okay. So if it is positive edge triggered, I have drawn the diagram for negative edges. So it's okay. So for me it's fine. But I guess if you have drawn, then you have to redraw it once again. Okay. So these are all the positive edges of the clock. Okay. So this is your positive edge of the clock. Now, if you have not noted, it's okay. You can note it later on. I will give you time to note. So look over here. Okay. Look over here. So over here, this is QA, this is QB, this is QC. So QA, initially QA, QB, QC, all are 0. Okay. All are 0. You can even initialize it with 1. It is up to you. Okay. You can initialize it with 0 0 0. 0, 0, 1, anything you want, it will come into your cyclic state after a while. Okay, so you can initialize it with 0, 0, 0, 0, 0, 1, 1, 1, 1, 1, 1, 0, anything you want, but the simplest way to initialize is either from 0, 0, 0 or from 1, 1, 1. So I am initializing it with 0, 0, 0. So you can see what, that over here I am drawing QA. This is your clock. So QA initially is 0. So the moment we get one active edge, so this will jump to 1, means it will toggle, and it will keep on toggling like this. Okay, so this toggling will go on. Now you can see what, that this QA is acting as your clock pulse for your B flip flop, and your B flip flop is a positive edge triggered flip flop. Okay, positive edge triggered flip flop. So basically the clock pulse will be QA. So mark the positive edges of QA. So all these are your positive edges of QA. So at this places, there will be toggling at the output of QB. So initially this was also 0. So this will go from 0 to 1 at this edge, and it will stay over here till the next edge. And this toggling will keep on continuing. Wait a minute. So over here, this toggling will keep on going. Now you can see basically this QB, it is actually your clock pulse for JC, means JC I am telling, your C flip flop, and C flip flop is a positive edge triggered flip flop. So basically the positive edges of QB will be acting as your trigger for JC. So JC means for JC I am telling, for QC or C flip flop. So again this has also started from 0. So it will go from 0 to 1. So first let us mark the positive edges. So this is one positive edge, this will be one more positive edge, and this is one more positive edge. So toggling will take place like this. This is one more toggling. Okay, fine. So now this is what, this is QC, and I have already told you MSB toggles the least, and your MSB is basically the flip flop that is farthest from the external clock. So this is farthest. So QC will be MSB and QA will be LSB. But look at the counting sequence. So this is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. This is 0, 1, 1, 0, 0, 1, 1, 0, 0, 1. Means next will be 1, 1. It's okay. So this will be 0, 1, 1, 1, 1, 0, 0, 0, 0, again 1. So you can see the counting states over here are from 0, 0, 0, then to 1, 1, 1, then to 1, 1, 0, then to 1, 0, 1, then to 0, sorry, then to 1, 0, 0, then to 0, 1, 1, then to 0, 1, 0, then to 0, 0, 1, and last 0, 0, 0, and once again 1, 1, sorry, 1, 1, 1. So your counting sequence, it is going something like this. If you take your counting from QC, QB, QA, so this will be what? It will be from 0, 0, 0. Means you can start it like this also, from 1, 1, 1, then to 110. So this is what? This is your mod 8 down counter. Okay, mod 8 down counter. Now if you had taken output from QC complement, QB complement, QA complement, then it would have been what? Just the complement of all the states. So this will be 0, 0, 0, 0, 0, 1, like this till 1, 1, 1, and again back to 0, 0, 0. So this will be mod 8 up counter. So first quickly note this down. First make the diagram properly and note down, and then we will discuss. Note. So this is what? This is your mod 8 counter. Now depending on from where we take actually your output, it will be either up counter or down counter. See, one thing you people note, either we take the clock pulse from all the positive output, means sorry, positive I am telling, non-complemented output. You can see everywhere I have taken from non-complemented, or you can even take the clock, means one more diagram you can draw, or you can take the clock like this. But you cannot take clock pulse, means if suppose you have taken negative over here, the negative of QB is acting as clock for this, you cannot take it like this. Okay. Such kind of cases is not possible. This is wrong. Okay, this is not possible. So either you take clock pulses from all the complemented output, or you take output from non-complemented output. You cannot have mixed clock pulses. Okay. Okay, fine. So now you can see one of the clock pulse has time period TCLK. So this is having time period 2 TCLK. This has what? This has QB has 4 TCLK, and QC has what? It has time period 8 TCLK. So if that is the case, over here if frequency is FCLK, so for here means for QA it will be FCLK by 2. Over here it will be FCLK by 2 to the power 2, that means 4, and over here it will be FCLK by 2 to the power 3, or 2 to the power means FCLK by 8. So sometimes this is also known as divide by 8. Divide by 8 counter. Okay, divide by 8 counter also sometimes it is known as. Is this clear, everyone? Clear? Any doubts? So remember this also, that you can have your clock pulses either from non-complemented output in all the subsequent stages, or you can have from complemented output in all the subsequent stages. You cannot have mixed clock pulses. Okay, that in some place you are taking from non-complement, some places you are taking from complement. Those cases will not be possible. Now you can see in synchronous counter, either the count sequence is up counting or down counting. Now basically, if in examination it is asked, So how are we going to determine whether it is counting up or whether it is counting down? So for that, we have one shortcut. Okay, we have one shortcut over here. So look over here. I have taken all the possibilities over here, that when you have negative edge triggered and you take your clock pulses from normal outputs, when you have positive edge trigger and you take output from your normal, if you have positive edge and you take output from your complemented output, and if you have negative edge triggered and you take output from basically complemented output. So basically there will be four combinations. How? See, there will be two combinations for edge. So edge can be either positive or negative, and there are there can be two possibilities of your clock pulse. Either it can be taken from your complemented variable or non-complemented. Okay. So that means in total we are going to have how many? We are going to have basically four four combinations we are going to have over here. So all the four combinations I have drawn. Now listen very carefully, then you can draw this. See, here I have assumed that your negative edge corresponds to negative sign. Okay, negative sign. Negative edge corresponds to negative sign, and positive edge corresponds to plus sign. Okay. Along with that, I have assumed that complemented variable, if we are taking your clock pulse from your complemented outputs, so that will correspond to negative sign. And if you take output from non-complemented variable, so that corresponds to positive sign. Okay, that corresponds to positive sign. Now, whenever we have opposite sign of what? Opposite sign of edge as well as variable, opposite sign, at that time your normal output will act as your up counter. If normal output acts as your up counter, then what? Then your your normal output, if it acts as your up counter, then your complemented output will act as your down counter. We have seen if one of the output, like in the previous cases, if this was acting as your up counter, then this were acting as what? These were acting as your down counter. So here I have just generalized this on the basis of normal output only. Then it will be easier to remember. And if we have same sign, same sign of what? Same sign of edge as well as variables, then your normal output will act as your down counter. Now with this concept, you can check over here that we are basically taking what? Negative edge. So negative edge corresponds to, you can see over here, minus, and we are taking output from non-complemented output, so that corresponds to plus. So say different sign means what? Different sign means if you take output from here, then it will be up counter. So in the first example, you can see, in the second example, you can see I have taken output from your non-complemented variable and it is negative edge. So that is why if I had taken this 2 as my output, it was acting as your up counter, 0 0, then 0 1, 1 0, 1 1. So this is up counter. Similarly, if you take output from this complemented, so this will be down. Now in the second case, you can see you are taking output from your non-complemented, so that is plus, and on top of that it is positive edge, so plus, same sign means If you take from non-complemented, it will be down counter, and if this is down, if you take output from here, so this will be up. Similarly, over here you can see you are taking output from negative edges, okay, means from your non-complement, and this is positive edge. So different sign. If different sign, then for normal output, we have what? We have up counter. And that means if we take output from here, this will be down. Similarly, over here you can see same sign we have. So if we take output from non-complemented, so this will be what? This will be down. And if we take output from here, this will be up. Tell me if this is clear or not. You can solve it. You can solve it later on. You can check for any of the case and you will get the result only. So instead of solving like this for 8 cases, we have just done it in your means with the help of trick. Okay. So this is one shortcut trick for determining basically up counter and down counter sequence. Tell me if this is clear or not. Is this clear? Anyone having any doubt? So I will say you check, means at your free time you can check anyone by taking any one of the concept. You can see whether it will be coming out to be as up counter or down counter. Tell me if this is clear or not. So note it down quickly. Okay. So now see, all the time basically we are counting what? Either when it is your up counter, we go from 0 to 1. Means if it is a 3-bit, we go from 0 to 1, then to 2, then 3, then 4, then 5, then 6, then 7, then again back to 0. Okay, so we have this count sequence. It is your, if it is your up counter, if it is your down counter, we go from 7 to 6, 5, 4, 3, 2, 1, 0, again back to 7. Okay, so if this is your down counter. But what if, suppose I want my count to look like this, 0 to 1, if it is your 3-bit. Okay, if it is your 3-bit, I want my count sequence to look like 0 to 1, then to 2, then to 3, then to 4, then to 5, then back to 0. I don't want 6 and 7 in my counting state. These should be a new state. So what can we do? Sir, still I have to, अरे कितना slow note करोगे? Note it quickly. So this will be the last topic for today, active clear and active preset. Okay. So now you can see what? If suppose I don't want this to count sequences, my sequence should have only this. Or if suppose in my down counter, I don't want this 2 sequence, this 3 sequence I don't want, only count sequence should be from 7, 6, 5, 4, then to 3, and then again back to 7, then how can I do it? Okay, how can I do it? So this is where we have asynchronous clear and preset input. Okay, asynchronous clear and preset input. So when we started this chapter, we started with a simple latch. Okay, we started with simple latch that looked like this. So this was our latch. Then we did what? We constructed a flip-flop by giving clock over here. Okay. Now we have something known as clear and preset input. So basically this clear and preset is fed over here. So this is one more input we have. Okay. Now what is the purpose of this clear and preset? Let us understand. Okay. So you can see this is your latch. Okay, so why have I drawn 2 over here? So it's okay. Okay. So look very carefully. So this was our latch. Now, in the first class, I never told you that with latch, we have this clear input and preset input also. Okay. Now, what does this clear and preset do? First, let us understand. So whenever, if you remember, if we have OR gate, sorry, NOR gate, if we have NOR gate. So I have told you that NOR gate is basically what? It is A plus B whole complement. Now, if one of the input of the NOR gate, if it is 1, okay, if it is 1, immediately what will happen? It will go to your 0. Output will be what? It will be 0. So in NOR gate, I have told you that your more priority is being given to 1. So this clear and preset, we will see what basically they do. So now look, the combination of clear and preset that we can have, either both of them will be 0, or clear 0, pre 1, or clear is 1, pre is 0, and clear is means both of them are 1 1. So these means 4 combinations we can have for clear and preset. Now look, when clear is 0, pre is 0, both of them 0. So what will happen? What will happen over here? So flip flop, it will, sorry, your latch, it will be working in your normal mode. Why? Because whenever it is 0, your latch has to check for other inputs. So basically your flip flop will be working in your hold state, or there will be no change. But look over here, this is A, this is B, or you can even write this as set and reset. I have told you opposite to complement, we have set, so this will be reset. Now if assume clear is 0 and pre is 1, second case. So the moment this pre is 1, what will happen? Output over here will be 0, irrespective of what is set, what is reset, we don't care. The moment one of the input of NOR gate is 1, its output will be 0. And if this is 0, this is 1. So what does this imply? That your next means normal output is 1 and complemented output is 0. So immediately, as your Qn plus 1 is equal to 1, so it will set your flip flop, set state. Immediately it will take your flip flop to set state. Now assume if if clear input is equal to 1 and pre input is equal to 0. What I said, clear input 1, pre is 0. So what will happen? If clear input is 1, immediately output over here will be 0. And if this is 0, this will go to 1. So you can see Qn plus 1 is equal to 0. So this is reset state. Reset state. Okay. And last is when both of them are 1 1. So if both of them are 1 1, so that is invalid state. So first tell me, have you understood this or not? Have you understood this? First tell me this. Have you understood this much? Tell me yes or no. Anyone have any doubt? Okay, fine.
Sir?
Yes, tell me.
Yeah. So, sir, here you take like clear is equal to 1 and preset equal to 0. Okay. So, sir, when you said preset equal to, it's if it's 1, then it's final, like Qn plus 1 will be 0. Okay, sir. But when you take preset equal to 0, then sir, it will depend on the S, na, sir. Like whatever the value of the S.
See, when this is 1, okay, if this is 1, so this will become 0. This 0 is latched over here. Okay. This 0 will latch over here. But we know what? Except for invalid state or hold state, if one of the input means whenever we had different input configuration, so at that time what we had, if one of the normal input is 0, so your complemented will be just the opposite of that one. Only at your hold case or at invalid case, we were actually depending on what means, sorry, only in your hold case when both the inputs are 0, at that time only we were waiting for other inputs. But here you can see one of the input is 1, another is 0. So whenever your inputs are at different stages or at different states, we don't look for your means input, any other input. If one of the output is 0, other will be 1 or vice versa. Did you understand this?
Yes, sir.
Okay, so only in case of your hold state we need to check. And hold state, when it happens, if it is your NOR latch, it will happen for 0 0, and in your NAND latch it will happen in 1 1. So at hold state only basically we need to check for your what is the other input conditions. Okay, so you have understood. Okay, first then let me tell you about this also. Okay, so this is your NAND latch. So in NAND latch you can see what, this is your pre, this is your clear. So again you can have 4 combinations, and we know what in NAND gate, basically if one of the input is 0, immediately your output will be 1. And I have already told you in NAND gate 0 is at high priority. Okay, so whenever both of them are 0 0, so at that case your flip flop will be working in your invalid mode. Now look, here I have taken clear bar and pre bar. Can anyone tell me why? Why I have taken clear bar, pre bar? Tell me, why have we taken clear bar and pre bar? Array, I told you just now. Over here 0 is at high priority. Okay, 0 is at high priority. So basically your flip flop will either go into set state or reset state when either of the clear or pre is equal to 0. And when we have to basically take, means whenever input corresponds to 0, at that time we take what, we take it in a negative logic or with a bar, because supplying 0 means what, we are basically giving input. So over here you can see clear bar is 0 and pre bar is 1. So supplying 0 means you are giving input. Why? Because when you give 0 over here, immediately this will go to 1, and if this is 1, so this is 0. So you are seeing what, you are giving input to clear. So your flip flop, you can see it is going to Qn plus 1 is equal to 0, that is reset state. And when your clear input is 1 and pre input is 0, so what will happen if this is 0, this will go to 1, this will go to 0. So Qn plus 1 is equal to 1. So this is set state. And the last case when both of them are 1 1, that will be your hold state. Okay. So here you can see basically when you give 0, when you give 0 to pre, you are setting the flip flop. When you are giving 0 to clear, you are doing what, you are resetting the flip flop. So here I should have written them clear bar and pre bar. Why? Because here giving 0 means you are giving input to the latch. So that is why these are active low. Tell me if this is clear or not. Is this clear? And one more thing you need to note, that have I written it? No. So clear and pre, it signifies that basically you are using NOR latches, and clear bar and pre bar signifies that you are using NAND latch. Now let us understand what do we mean by this means clear and pre. So look over here, when we were at this case, okay. So this was what? This was QC, QB, and QA. So we were counting like this from 0, 0, 0 to 0, 0, 1, then to 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1. The next state is what? It is 1, 1, 0. But we want our flip-flop to go to this state. But look over here. After 1, 0, 1, the next state is what? It is the next natural state is 1, 1, 0. So basically, if I do what? If I do QC is equal to QB is equal to 0, that means what? If I clear the state of QC, QB, or if I reset first, this second, if I reset QB and QA flip-flop, flip-flop B and flip-flop C at this. So this, if this is your first clock pulse, second clock pulse, third, fourth, fifth, sixth. So at seventh clock pulse, if I clear the state of QC, QB, or if I reset flip-flop B and flip-flop C, what will happen? Instead of going to 1, 1, 0, it will go to 0, 0, 0. So this is where clear comes into play. So clear, when does it comes into play? That when basically you have to clear the state of flip-flop in your up counter. Similarly, you can use clear bar also. So I should have written over here, clear the state of QC, QB. And how can we achieve that? We can achieve that with your input clear or clear bar. With the help of this two input, we can achieve this. So over here, I should have written clear. Okay, clear the state of QC, QB. So that can be done using either clear or clear complement. Tell me if this is clear or not. So clear we always use with up counter always. Now look for preset. So what I told you, I want this counting sequence. So let us assume this is first clock pulse, second, third, fourth, fifth. Okay. So your natural count of this down counter after this fifth clock pulse is what? That from 0, 1, 1, it should go to, means 0, 1, 1, it should go to 0, 1, 0. But what I want basically, if this is your QC, QB, QA, after this fifth, I don't want to go to this state. I directly want to go over here. So how can I achieve that? So you can see basically QB and QA are already one. If I just do what? If I set the state of QC equal to 1, or what I do, basically I set QC flip-flop, okay, then I will be able to go where? I will be able to go to QC, QB, QA equal to 1, 1, 1. So basically I am doing what? I am setting this C flip-flop. So this we can use, we can get using either pre or pre-complement. So I am presetting the, I should have written preset the state of QC to 1. So this can be achieved using pre or pre-complement. So remember, this we always use with your down counter. Tell me if this is clear or not. Is this clear? So we will stop over here because this is enough for today. So in the next session, we will go ahead. So tell me if this is understood by you or not. Whatever I said right now. Any doubts, anyone? Any doubts? So we will be